So far today we've been talking about binary trees where we have a root node and then each node can have a left subtree or can have a left child. It can also have a right child, and the left child or right child can also have left or right child nodes. And we have another data structure called heap. In a heap, well, of course, heap is a binary tree. And there are some other requirements to make a binary tree a valid heap. The first requirement is that in a maximum heap, so let's talk about maximum heap today because minimum heap will be similar. In a maximum heap, a parent node will have a value greater than its children nodes, or at least not smaller than children nodes. For example, if you have 9 as the root node of a heap, then if it has 2 children nodes, these 2 nodes must have values no greater than 9. For example, we can have 6 and 8. Now, this is a valid maximum heap because for all the parent node, the parent node has a value larger than or at least no smaller than children nodes. Right, so this is the first requirement. In maximum heap, parent node should have a value no smaller than the children nodes. Then the second requirement is that in a heap, all the nodes must be ordered from left to right, ordered level by level, and within each level from left to right. For example, if we have one single node in the heap, then it must be like this, well, the root node, of course. And if we want to add the second node into the heap, the only possibility is we add it as the left child. We cannot add a node into the right as the right child if we don't have the left child yet. So remember, nodes are ordered from level by level. So the first level we have one single node 9, and in the second level we can have 2 nodes, and if we want to add one, we must add a node from left to right. So node 8, if we want to add, we have to place it here. So that's the second requirement. Second requirement, the nodes has to be ordered level by level and within each level from left to right. So that's it, the 2 requirements for a maximum heap. And in order to create a maximum heap, I think we've discussed at least 2 different approaches. The first one is let's insert each element one by one into an existing heap, and at the beginning the heap is empty. So for this case, we have ALGORITHM 9 elements in total. If we add them one by one, so the first element we're going to add is node A. Then the second element, so each time when we add an element, we add to the next available position. So L will be added as the left child of A. And every time after adding the element, we're going to have the newly added element compared with its parent node. If it's larger than the parent, we're going to swap these 2 elements. Clearly, this is the case. L is larger than A, so we're going to perform a swap so that L will be the root node and A become its left subtree, left child node. Now, this is a valid maximum heap containing 2 nodes. So the next step is we're going to add the next node, G. So G will be added here, next available position. And then we're going to have this newly added element G compared with its parent L. G is smaller than L, so no swaps need to be performed. Next one, O. So the next available position is here as the left child of A. And we compare O with its parent node A, noticing that we need to perform a swap. And remember that after performing the swap, we still need to have this newly added element compared with its parent node. In this case, we want to have O compared with L. O is larger than L, so we need another swap. So O will become the root node, and L comes here. And for the next node, R is added here, and compare R with its with its parent node. We're going to swap R with L. Then we will have R compared with O, and since R is larger, we're going to also make another swap. And now since R is at the root node, having no parent node anymore, no more swaps, no more comparisons, no more swaps. And then next node is I, so we add it as a left child of G and then compared with G, and we need a swap. So we repeat this until we have all the elements added into this maximum heap. And as discussed, each time after adding the element, the worst case is that we may need to have the newly added element swapped to the root node of the entire heap. Requires roughly log n number of swaps, which is the number of levels in this tree or in this heap. And since we might need to perform, since for each of the nodes, the worst case is that we might need to perform that many number of swaps. So this would be the time complexity for constructing the heap by inserting elements one by one into an empty heap. You might wonder, for the first few nodes, we definitely don't need to have log n number of swaps, because for the first few nodes, the height of the tree is very small. But if you consider the last few nodes, or last half of the nodes being inserted into the tree, say if we have into the heap. If we have a heap containing, I don't know, n number of nodes in total, then if you try to find out how many nodes are there in the last level, in the bottom level, or in the second last level, you will find that the number of leaf nodes in this heap is roughly half of n. And for all of them, the worst case would be log n number of swaps. So if we only consider the number of swaps needed for the last half of the elements added into the heap, we already need that many swaps, which is already in n log n. So time complexity for this approach we have the second approach for the heap, which is the bottom-up approach, question 56. So the idea here is that we are not going to insert each of our elements one by one into a heap to making the comparisons and then do the swaps. But instead, we first try to construct a binary tree, which is the heap. So we're going to have A, L, G, O,